Okay, when you hear the word polar, you normally think about ends. Okay, ends of the Earth, North Pole, South Pole, positive end, negative end of the magnet. That's what you're thinking of when you hear the word pole. Well, the same thing comes in when we're talking about bond polarity. Okay, to talk about bond polarity, we need to bring back our good old friend electronegativity. So, reminder, electronegativity, the willingness to take an electron from another atom. And it's on a scale of 0.7 to 4. 4 being the highest electronegativity, fluorine, and 0.7 being the lowest, cesium. So remember the trends here for electronegativity. So when we talk about a bond, especially a covalent bond here, or actually any bond, it's really a combination of characteristics between both ionic and covalent bonds. Okay, and what leads us to the different kinds of bonds is the difference in electronegativity. Okay, so if we look over here on our nice chart here, percentage of ionic characteristics, right? If you look right around here, okay, which is the difference in electronegativity here, everything above 50% we call ionic. Okay, and then we get into these two terms down here we're going to talk a little bit more about. So covalent bonds can be broken down into polar and non-polar covalent bonds. So let's talk a little bit more about those here. Okay, so if we look here, we've got two chlorine atoms combining together here, diatomic molecule, right? And here we have oxygen and two hydrogens forming water. Both of these are both of these are covalent bonds, so they're sharing electrons. This top one here is what we call a non-polar covalent. There are no charges associated with this. Electrons are shared completely evenly. Down here we call this a polar covalent bond. Okay, really and truly, between hydrogen and oxygen, we're going to talk that this isn't really a fair share of electrons. We keep talking about them being shared, but really one of them pulls a little bit harder than the other. Okay, and we're going to use these symbols here to represent which one is partially positive and which one is partially negative here. So, as we're looking at these, okay, when we evaluate a bond, okay, when we evaluate the bond, we're looking at the differences in electronegativity, like we've mentioned. Right? The one with the higher the electronegativity is going to have this funky little symbol here, which is partially negative, because it is more likely to pull the negative electron. So the one that doesn't get as much of the negative electron has this little symbol here that we have as a partial positive, because it doesn't get the electron not quite as much. That's why it has the lower electronegativity. Let's see this written here. Okay, here's an example of hydrochloric acid. Right? It's a covalent bond here between hydrogen and chlorine. Well, chlorine has a higher electronegativity. So really and truly, when it shares electrons, it's pulled more towards the chlorine than it is the hydrogen. That's why we have this symbol right here showing the partial negative compared to the partial positive. Now this is going to become more important as time goes on, but we're going to wait till after break to really get into that. So we talked about nonpolar and polar. Okay, so first of all, a nonpolar covalent bond. Right, the electrons are shared equally. So it's really a symmetrical electron density, meaning that you're not as, the chances of you finding electron in a particular place is just as good at any location around the bond. Okay, normally these are identical atoms. Normally, we're going to find some cases in which that's not the case, but we'll talk about that here in a minute. Okay, but here, if we look at this example here, we've got our two nuclei, right, and we see that it's equally distributed here. Right, we have just as good of chance of finding an electron here, this distance away from this nucleus, as we do this distance away from this nucleus. Okay, diatomic elements are nonpolar, but we're dealing with bonds themselves here. Okay, we'll get into whole molecules later as to a polar and nonpolar molecule, but right now we're just talking about bonds themselves. Okay, then we have polar bonds, where the electrons are not shared equally. Okay, an asymmetrical electron density. Let's look at that. See, here we've got our partial negative and our partial positive. This is the one that has a higher electronegativity. Since it has a higher electronegativity, it's more likely to pull that electron. So if you see, you have a better chance of finding the electron around this atom here in this end of the bond than you do this end of the bond. Okay, so we result in what we call a partial charge, and that's what this little symbol here indicates. Okay, a partial negative, the one with a higher electronegativity, and a partial positive, the one with the lower electronegativity. Okay, let's look at this one other way here as well, a little bit more fun way. All right, kind of putting all these together. So we've got our nonpolar bond. In come a couple of dogs. Notice they're the same dog, fighting over those bones. And look, they share. One of them can't pull any harder than the other, right? So they're sharing equally. So this is a nonpolar bond, an example, right? Chlorine here, diatomic element. Okay, a polar bond, an unequal share. Right? Look at this. We got a little bit bigger dog here compared to that one. So they come, they get in a fight, and one's pulling a little bit harder than the other. Right? One can pull just a little bit harder than the other there between those two. And then we've got an ionic bond. Right? Here, a fight breaks out. One dog wins them both. Right? Aw, but they are kind of attracted. That little dog is still attracted, right? Right? The electrostatic charge. Right? But here we see an even sharing between the two. Here we see a share, but one takes a little bit more than the other. And then here we see one just completely rips the electron away from the other there. Right? So nonpolar, polar, and ionic. Right? So how can we tell the true difference between these? Here's where you need to grab the periodic table that I gave you, well, either yesterday or you just got today, depending on the class here. Right? On those periodic tables in the bottom right-hand corner, you have the electronegativity of every atom on the periodic table. What we are interested in is the difference between the electronegativities. So you look up chlorine on the periodic table, and you see that it has an electronegativity of 3. Well, the difference between the two of them in that bond is 0. Right? So that's a nonpolar bond. Right? The difference being down here, 0. Look up hydrogen and chlorine. Oh, sorry, nonpolar. Hydrogen and chlorine. Okay. Chlorine has an electronegativity of 3. Hydrogen has an electronegativity of 2.1. So the difference is 0.9. Right? Well, when we look here, kind of looking at our scale here, I'll actually give you some real numbers here in just a moment, but looking at our scale here, we see that this is squarely in the polar covalent. So this is a polar covalent bond. The electrons are shared, but the chlorine is pulling just a little bit harder than the hydrogen here. Okay, and then we have sodium chloride. Right, so our 3 electronegativity for the chlorine and our 0.9 for sodium, really low electronegativity. Right, the difference is a 2.1. That's a big difference in electronegativities. Okay, one really wants to take the electron, and one really doesn't want to take the electron. In fact, so much that it has a low ionization energy and really wants to get rid of that thing. So when we look at a 2.1 up here, that is in our ionic scale or range, right? So that is an ionic bond. Great, wonderful. Could I have some real numbers to go with this instead of having to look at this chart every time? Why, certainly, of course you can. So, how do we really determine the type of bond then? Let's look at some real numbers. Okay, so first of all, we find the electronegativity difference. Okay, difference, electronegativity. Right? If the difference between the two is less than 0.5, we call it a nonpolar bond. Okay? If the difference is between 0.5 and 1.6, the bond is polar. Okay? And if the difference between the two is greater than 2, then we say the bond is ionic. All right? So, 0.5, 0.5 to 1.6, 2. There's a little jump in here between 1.6 and 2, right? What about that gap? So, here we go. Right? If the difference is between 1.6 and 2, if there's a metal and a nonmetal, we consider that ionic. Right? If we have a metal and a nonmetal, it's ionic. If there are two nonmetals that are involved, then we consider it a polar bond. It's as simple as that. Okay, so now what I'd like for you to do is go back to the homework that we did the last couple of days, and also the one that you just got today. And I want you to try to assign partial charges and try to distinguish each bond as polar or nonpolar inside of each molecule that you are looking at. Okay. We will then take this another step further then on, well, after break here. Okay, and really talk about polar and nonpolar molecules. Not just bonds themselves, but the molecule overall. All right. If you guys have any questions, send me emails, or we will talk tomorrow in class. So have a wonderful day. Bye.